So, the police officer is 30 feet away from the road. So that's this side right here. And at the time that the car is radared, the car is 100 feet away from the police officer. But is that distance remaining the same? No, because the car is moving in this direction down the road. So I can't label side C here as 100 because side C is only 100 at that moment in time, right? So we would, if this is a straight road, we would assume that this is a right triangle. And so the police car is not moving, so side A of this triangle is always 30, right? Side A is not changing. So we can say that 30 squared plus B squared equals C squared. Okay, so if I take a derivative of this equation, in this case, what I want to do is take the derivative with respect to time. Okay? Time is not a variable in this equation that I have here, right? Normally, when we take the derivative with respect to x. Usually x is the variable in the equation, so we don't do anything. Or, remember in implicit differentiation, sometimes we had a y, and we had to take the derivative of y, so we had to put dy dx because we weren't taking the derivative of the variable that we were taking the derivative with respect to. So, I want to take the derivative of this function with respect to time. The reason that I want to do that is because if I take the derivative of b with respect to time, that is going to give me db over dt. B is measured in feet. We're going to do time in seconds. So that would give me dB dt, which is the length B is changing in feet per second. That's how fast the car is going, right? Because the length that B is changing is how far it's going down the road. So the rate of change of that length is the speed of the car. But the radar gun is hitting the car from this angle. The radar gun is measuring C and seeing how far C is going, C is changing, right? So dC dt is also a speed in feet per second, but is it the speed of the car? It is not, because the car is going down the road, right? The speed that B is changing is the speed of the car. The rate that C is changing is not the speed of the car. It's going to be slightly different there. So we're going to take the derivative of this function with respect to time. Okay, it works very much like implicit differentiation. The only difference is we're taking the derivative of the variables here with respect to a variable that's not in the problem at all. So anytime we take any derivative, we're going to need to put like a dB dt or a dC dt, or if there was a z, a dz dt, with anything we take the derivative of. All right. So the only thing you don't need to take a derivative with respect, put a dt with, is if you had a t in the problem, but we don't. So I'm going to take the derivative. Derivative of 30 squared is just 0. It goes away. That's just a constant, right? And so I've got 2b dB dt, and I've got 2c dC dt. very much like implicit differentiation, but in implicit differentiation, if we take the derivative of x, we don't have to do anything with it. With related rate problems, the variable you're taking the derivative of, or derivative with respect to, is not in the problem, so everything is going to need the dt with it there. So once we get this, we're going to plug in the information that we know. So at this point, I can plug in information that I know that happens at this particular instant, right? So I can't do it before I take the derivative, but I can plug in things like my 100 feet now, right? So 100 feet is c. So I'm going to have 2 times 100. And the speed of the car, the speed of the car is dB dt. The radar gun is seeing how fast the car is moving away from the radar gun here. So that is, we want to use the 103 right there because our measurements are in feet right here. So we don't want to use 70 because that is measured in miles per hour. So it's not the same units that we're using. So we'll take very slightly, I think. I can't remember the answer to this, but I think we're going to be off just a little, right? There. Now, 2 definitely stays here. I don't know dB dt. That's what I'm trying to find. dB dt is the speed of the car. It's the rate of change of b. That's the speed of the car. B I don't have, but at this instant, this side right here was 100. Can I find B at that instant? I could just do Pythagorean theorem, right? So I could say 30 squared plus B squared equals 100 squared. So we got 900 plus B squared equals 10,000. Is that right? No, I think I need another 30 times 30. No, that's right. Okay. Yeah. And I'll subtract my 900. So B squared equals 9,100. And then I need to take the square root of that. And that, these are going to be calculator active problems, as pretty much any real world problem ends up having to be. So I am getting that B is 95.39. So I've got 2 times that 95.3939 dB dt. Right. Now I just need to, I'm going to need the calculator, but I just have like a pretty straightforward problem for solving this. So if I multiply 2 times that 95.3939, I get 190.788 dB dt, and that's going to equal 2 times 100 times 103 is 20600. And last step, I just have to divide here. And dB dt is going to be 107.973. And that B is measured in feet, so that is feet per second. So the radar gun, assuming it's not accounting for this, and maybe the programmers of the radar gun like have angles and stuff in there where it accounts for this automatically. If so, the person who works for the radar gun company that programs it to know what angle and all of that, they are using a lot of calculus. And that's probably one person, maybe two, so somebody checks to make sure they do it right. If it automatically accounts. If it doesn't account for this, does it really matter as far as pulling somebody over? The radar gun said that the car was going 103 feet per second. How fast was the car actually going? 107.937. So the car was actually going faster than the radar gun said that it was going anyway. So it's not like you could go to court. Who would go to court and be like, I was going faster than this. I deserve more punishment than you have given me, right? Like nobody would do that. So it actually ends up being not that important in this particular case. And then we change it back to miles per hour, and it's probably even more of like a negligible amount that we're looking at here, maybe a mile or two per hour, where this is not a huge deal. So I would imagine, unless the radar gun accounts for it automatically, I'm certain nobody's sitting down and figuring this out. However, if we think about this, definitely here, like we wouldn't need to really worry about it. I've given you this scenario because it is something we can relate to. You know, we've had a lot of cops pulling people over for speeding sort of problems, right? It's like something we can relate to because we understand it. We can picture it. We can see what's happening here. But if we were in a much more precise environment, I am not a scientist or a mechanical engineer or like somebody where I imagine maybe this would be used. But if you were taking measurements using some sort of sensor and this was happening, it could affect like maybe whatever experiment that you were doing significantly if it's something that has a very, very low margin of error, right? So, so I could imagine places where this would be really necessary for somebody to consider. Now, I feel like if you're doing that, you're working in some sort of like lab somewhere, designing, creating, like doing some like high level stuff. I don't know, I wish that I knew somebody that had like a job building roller coasters or working on F1 cars or something, like some of the stuff where they really get crazy with like how they are analyzing everything there, just to know, like, are you using any of this stuff? Show me what you do. But unfortunately, I do not know anybody that has a job quite that cool. So if you know anybody, send them my way, because I think that would be super cool. The only problem is that to do that at that level, you have to be such an expert that it becomes difficult for you to explain because there's more variables and things that you have to consider. So, if you want jobs like that, if you want to work for NASA, if you want to, be analyzing the F1 cars, if you want to build roller coasters, this is only the beginning for you. These are baby steps. They would look at what we're doing here and laugh, right? But you got to know this to get higher. Again, there's not that many jobs in the world that do that. They exist. And in my imagination, somebody is using this somewhere, but I'd love to know them. And maybe the computer does it all. Maybe it's only the computer engineer that sets up the software. I mean, somebody's got to tell the computer what to do. So somebody knows how to do it. Maybe, I don't know, maybe AI is coming up with it all now. Maybe we're no longer valid. I don't know, but it's AI makes a scary world. I tell you, like, I think more and more, like, should we all become plumbers? Mm-mm. Was it today? Was AI generated broadcast? I did not watch it because I don't have a VHS. I have to go back and look at it. That's interesting. Yeah. Yeah. Because AI music is crazy. Like, it's not as good as real music most of the time. But it's definitely better than an amateur musician. Like, it's crazy. And I've seen Elon's robot try to fold a shirt, and it's not very good at it. Unfortunately, it's not going to take away all the tasks that I don't want to do. But I'm afraid it might take away some of the things we do want to do. And I don't see him being able to install a toilet anytime soon using AI. Now, it might change like some of the technology plumbers use. But like, are we entering a world where like, and I don't see things like being a doctor. Like, you still need a person. Like, I think doctors can, like, it might help research and stuff like that a lot, but, like, I don't want to chatbot. I had to chatbot the stupid insurance company the other day. And it finally, after I answered all of its questions wrong, it was like, would you like to speak to a representative? Yes, please. And so then all I was able to do was complain about the actual person that was supposed to call me not calling me. And then so the person I was chatting had to send in a complaint basically. And then the lady called me within an hour. So, but then I can't talk to her because, well, I can, but like I can't make any decisions because the car's in Todd's name and not mine. Which I did because I didn't want to have to get, like, if you sell it or whenever you buy it, like, you both have to be there to sign it off. And I didn't want to miss working. So, like, I don't care. Just put it in your name. It doesn't matter. But now they won't let me do anything. Yeah, I mean, like, well, I probably could. But, see, he's got to go, like, he's in a meeting this afternoon. He has to go, like, inspect jobs. Like, so I'm available at the same time every day. He is not necessarily going to be available when I'm available. So I think what I need to do next time is put it only in my name, since it's my car. And then his name's not on it, so he doesn't have to be there for everything. Because he doesn't care about this as much as I do. Because his car's fine. But That's a side note. All right, let's look at some very basic general problems now. So I wanted to start off with an application problem so that you could see how the rate that this one piece is changing is affected by the rate the other piece is changing, but they're not necessarily the same depending on what criteria you have, right? That's the idea. But what we're practicing today, and if we don't get, the last one's also an application problem, but if we don't get to it, and you know how we are, we're probably not going to get to it. If we don't get to it, it's fine. Your homework is going to look like example 2 today. But I didn't want to start with that because it's terribly boring, right? It is a little easier, but it is terribly boring. And I wanted you to sort of see right off where we're going with this. But tonight, we're just going to practice the mechanics of taking a derivative with respect to a different variable, right? So if we have the equation y equals x squared plus 3, we are supposed to find dy dt when x equals 1 if dx dt equals 2 when x equals 1. Okay? So, in this case, they are giving us several pieces of information. Now, both of these pieces of information that they give us, we know dy dt, we're supposed to find dy dt when x equals 1, if dx dt equals 2 when x equals 1. Both of these have the condition that x equals 1. X doesn't always equal 1, but it's the point that we're looking at, right? So we can't plug it in before we take the derivative. In fact, there is nothing we can plug in before we take the derivative here because everything that they're telling us or asking us is contingent on the fact that x equals 1, right? Just like that 100, we could not plug it in before we took the derivative because that value was changing. So we took the derivative first, and then we said, but we really care about this one point where b equals 100, so now we're going to plug it in. So pretty much on all the ones you're going to do here, you're not going to have any information you can plug in before you take the derivative. When we get to the application problems, we'll see some things like that 30 that we could plug in. We're going to take the derivative of this function with respect to t. I'm using t because it says find dy dt, right? So I'm taking the derivative of y with respect to t. So when I take the derivative of y right here, I get dy dt. And then I'm going to take the derivative of x squared. That is 2x. But when we're doing related rate problems, we're taking the derivative with respect to a variable that's not in the problem. So everything needs the d whatever dt with it, right? So in this case, it's a dx dt. Very similar to implicit differentiation, but not exactly the same. And then the derivative of 3 is 0, so it doesn't need anything there. Okay? So we take the derivative with respect to t. That's our first step. Then you want to plug in the information that you have, right? So we are supposed to find, it says find dy dt. So dy dt is right here. That's what we're looking for. We are not going to replace dy dt with anything. That's what we're trying to find. We are hoping we have the other pieces so that we can plug those in. So I know x equals 1 is the condition we're looking at for both places. So I can replace the x with 1. So we got 2 times 1. And then at x equals 1, they tell me that the dx dt is 2. So I can replace the x dt with 2. So dy dt equals 4. And it is probably in your best interest to write out here when x equals 1. Because dy dt is not constant. It's not the same at all points. That is your rate of change of your y. It's not constant. It's not 4 at all points. But when x equals 1, it equals 4. Okay? Questions?
So every time you take the derivative of like a variable, you have to have the...
Correct. All right. So it's like implicit differentiation where we had to do the dy dx with everything, but we're doing d whatever the letter is over dt. It's usually t. It doesn't have to be t. Like you could find dy dA. When we get to application problems, your other variable is almost always time. So that's why we use t so much. But it could be a different letter where you have like dy dA and dx dA, but you're unlikely to see that. It'll probably be t's. All right, so this one's just slightly more difficult. Not much at all. We have x squared plus y squared equals 16. What is that the graph of? If we graphed it, what would it look like? Circle with a radius of, not 16, 4. Because that's x squared plus y squared equals radius squared, right? So this is the graph of a circle. We're going to take the derivative with respect to t because they're talking about dx dt and dy dt, right? So we're going to get 2x dx dt plus 2y dy dt. And the derivative of 16 is 0 because that is just a constant. So once we have this, we're going to plug things in. The question says to find dx dt. So dx dt does not get replaced. That's what we're looking for. I know that it tells me that x equals 4 and dy dt equals 3. So I got 2 times 4. And then I got my dx dt, which I do not want to replace. But, oh, I'm running into a problem here. I've got the y, I don't know what to replace it with, right? But I do know dy dt is 3. And I'm not going to be able to solve for the dx dt that's right here if I also have a y over here. So there's got to be some way for us to replace that y. What do you guys think? Any ideas? If we take that 4 and plug that into the original equation, that's what we were doing on the cop car radar situation problem, right? We took 100, we plugged it in so we could find B, right? So this is essentially sort of the same thing. So if you have a number that you can't replace, you could probably plug the x or y value, whichever one they've given you, into the original and find that other value. Now, you won't be able to do it, like, there shouldn't ever be a dy dt or a dx dt missing, except for the one you're looking for, because you're not going to be able to calculate that. We are going to sneak over here to the side. We're going to say 4 squared plus y squared equals 16. This is a weird problem. 16 plus y squared equals 16. I subtract 16. What's my y going to be? 0. So y is 0. It's kind of a weird problem, right? So if that is 0, I've got 8 dx dt equals 0. And then I need to divide by 8 here. And so dx dt is 0. And I think it's a good idea to put when x equals 4. Right there. I don't like 0 to be the answer, especially in something like this, but it is. So it's okay. 0 is a number. It's not undefined or anything. There. All right. So let's see. 11:45. Okay, we're okay. Okay, let's do a harder one. Okay. It's not really harder because of anything about the related rates part of it. It's just a more complicated equation that you're going to see. So really, the steps that we do every time: take the derivative with respect to t, plug in the information that you know. You might have to go over to the other side and find some extra information by plugging back into the original, and then solving for what they're asking you for. Like, those steps stay the same every time, even if if it's an easy problem like the first one that we looked at, or if it's a hard problem. This is one of the great things about calculus. I don't have to try as hard for us to review in this class, because when we take the derivative right here for 2xy, what have we got to do? Product rule, right? So we have to use a product rule. I'm going to treat this as a 2x and a y right here. You also could just keep the 2 out front, deal with it however you would like. So I've got 2x times the derivative of y, which is dy dt. Remember, we're doing a related rate problem here because I see a dy dt and a dx dt over here, not a dy dx. It's sometimes easy to get these mixed up with dy dx problems, right? But the question's not asking about or giving anything about dy dx. It's got a dy dt, which indicates related rates. So 2x dy dt plus y times the derivative of 2x, which is 2, but you must put a dx dt with that. So that's the derivative of just that little first piece. We got 2y, this one needs a dy dt, and that's going to equal 8. And even though the x went away, it had an x with it, so we still have to put a dx dt right here. So I'm going to highlight here, it says find dy dt. So I'm looking for dy dt. I've got two of them, but I think once we plug some numbers in, it's okay. We're going to be able to combine those, right? And then I know that y equals 1. So y equals 1, I'm going to be able to replace that y and that y with a 1. I'm going to be able to replace dx dt with 5. So dx dt is in both of these places with 5. Do you guys see, like, once I plug things in, do you see trouble? Something we haven't replaced here. This x, that x right there, it didn't give it to me. And I need to replace it because that yellow, the dy dt, that's what I'm trying to find. So this is a problem like the last one. We need to go plug y into this equation, okay, into this original equation. So over to the side, we are going to say 2x times 1 plus 1 squared equals 8x. So that gives me 2x plus 1 equals 8x. I'm going to subtract 2x right here. 1 equals 6x. And I'm a little annoyed, but I'm at least getting an answer. I got a fraction. 1/6 is our x. So other than having to have a fraction, which is a little bit annoying, we have that value. We can now plug this in for our x. So at this point, you're just plugging numbers in. 2 times 1/6 dy dt plus the y's 1, so 1 times 2 times dx, no, dx dt is 5, sorry, dy dt is 4, times 5, plus 2 times 1, dy dt is what we're solving for, so we won't leave it here, equals 8 times 5. There. So it's not as bad as it looks. I've got 2 times 1/6, that is like 2 over 1 times 1 over 6. That's 2/6, but that reduces to 1/3. So I've got 1/3 dy dt plus 10 plus 2 dy dt equals 40. Starting to get a little easier. You can definitely subtract that 10 to get 30 right here. And then that leaves you with 1/3 dy dt plus 2 dy dt. You can combine those. One of them is a fraction, but it's not that bad. So you're doing 1/3 plus 2. Got to have common denominators for that, so you'll multiply by 3 on top and bottom here. 1/3 plus 6/3 is going to give you 7/3. So I have 7/3 dy dt equals 30. We are dividing by 7/3 here, but dividing fractions is easy as pie. You can flip the second and multiply. So what I would do is I would multiply by 3 over 7 to avoid having to write out an extra step for that. And so your dy dt is going to equal 90 over 7 when, was it y equals 1 was the piece of information we had right there. Okay. Questions? All right. Our last one, well, let's do it. I mean, you got 5 minutes, so you're not going to start on the homework if I give it to you right now anyway. So Your homework is going to look like those three or four problems that we just did, right? So it is not going to be an application problem. But let's go ahead and do this one now because we don't really have time to start on the homework right now anyway. So in a rectangle, length is 8 foot longer than the width. So length is 8 foot longer than the width plus 8, right? The length of the rectangle is changing. When L equals 5, the LDT equals 5 feet per second. Find the rate at which the area is changing when L equals 5. So I know this equation, but is it asking me anything about the width? It's asking me about the area. Area of a rectangle equals length times width. But I really need an equation where I have all L's over here, because they did tell me what L is and dl dt. I could change this to all W's, but I don't want to do that because they gave me dl dt. They did not give me dw dt. So if I want to change this to all L's, what if I solve this equation right here for W? I'm going to subtract the 8. Right? L minus 8 equals W. If I do that, then I could replace W with this, right? So I've got area equals L times L minus 8. And it's asking me for the rate at which the area is changing. That's the rate of change of area. This is asking me to find dA dt. Right, that's what I'm looking for here. So what I would probably do first is I would distribute those L's. So I'd have L squared minus 8L. Just makes your derivative a little bit easier. And then I could take the derivative at this point, all right, with respect to t. So I would have dA dt equals 2L dl dt minus 8 dl dt. Everybody okay here? Okay, if you can get to this point, setup is the hardest on this. Sometimes the derivative is difficult depending on what type of problem you have. This one had a pretty easy derivative. If you can get to this point, you should not have too much trouble because you're just plugging numbers in, right? We're finding dA dt, so dA dt is what we're trying to find. We are not replacing dA dt. So we got dA dt. They told us that L was 5. They told us that the LDT was also 5. And so I got 8 times 5 here. So I've got 50 minus 40, and I get 10. Now, I do need to put units on this. I think, did they give us units? Yeah, they gave us feet and seconds, right? So this is the rate of change of area with respect to time, right? Area, in this case, is measured not in feet, but square feet, right? And time is measured in seconds, so square feet per second. For that. So, again, homework won't have you doing this. We're going to practice more with that. So if I went too fast or you're confused, we're going to do some more. Your assignment is really, I want you to do 1 through 8. but only do part A. It has you doing like the same problem several times with different like numbers to plug in. So I'm only going to make you do part A on those. Some of them should be super quick. Others might be just a little more challenging because they're more difficult equations. But they're all just like naked problems there.